Right, so solving equations. For a box with a length L and width W, the one you've just been doing in other words, we had a situation where the length is twice the width. So if I multiply the width by 1.5, I get the length, which is what Sophie did effectively. And I also know that the perimeter of this thing, so let's use P to represent the perimeter. Remember, P doesn't mean perimeter. P stands for a number, which is the perimeter, equals surely 2 times the width plus 2 times the length. So maybe more formally, I would write this. I've got 2 equations I can write from the information I was given. I'm told that the perimeter is 40, and I'm told that the length is 1.5 times the width. So I can write that information down as a formula, as a recipe. How do I get the length? I multiply the width by 1.5. There. How do I get the perimeter? I double the width, double the length, and add them together. So these effectively are formulae. So formulae are like recipes, if you like, ways to find L and W in this case. I can't find L and W and P in this formula as it stands. I need more information, which I'm given, but there's a recipe, there's a formula, and you will, as we've said already, end up with loads of formulae. We've been looking some in engineering science. But what I can do in this situation is sort of turn these formulae into equations, really. The first one, well, I just know that's some information, 1.5 W equals L, but the last one I can write that 2W plus 2L equals 40. But I know that L in here equals 1.5 W. So one of the things we can do is substitute in, which is what Sophie did. Instead of writing L, write 1.5 W. So I can write 2W plus 2 times 1.5 W equals 40. See what I've done there? I've replaced L with 1.5 W. And the use of a bracket is common there. And then I can write 2W plus, what's 2 times 1.5? 3W equals 40. And this is where Sophie came in. You sort of jumped to this point, didn't you, really? And then said, OK, well, what's 2W plus 3W? Remember, W is a number. 2 lots of that number plus 3 lots of that number from what we were talking about last week, basic algebra ideas, surely is 5W. And that equals 40. So if 5 lots of W equal 40, how do I get W? I divide both sides by 5 to get W equals, it's 40 divided by 5, 8. Thank you. Okay. And then I can carry on and get the other one. So in that case, I could work it out for a perimeter of 40. And whatever perimeter I have, I've got a way of solving the equation. So I need to be able to form equations, solve them using these steps. So these steps to get to the answer is what I'm going to focus on now. What we do is we think about this, and I'm sure you've seen this sort of idea before at school, this idea of a seesaw. And this is the pivot. So it ties in quite nicely with the engineering we're doing at the moment. And what we're saying in the equation is that this equal sign here means that that side of the equation balances that side of the equation. And the whole idea is to say to yourself, if I want to simplify one side of the equation, say this side of the equation, which might be something like this, I can simplify it by getting rid of things. Say I was interested in finding out what W was. I go through steps to get rid of the rest of what's on here. I want to get rid of the 2L and want to get rid of the 2, so I'm just left with W. And how I do that is by manipulating the both sides of the equation. I do something to this side, so I end up with what I want. Remember, though, that whatever I do to this side, I must also do to that side, and that's the key. And it's whether it's an equation or a formula, that's what we do. You can't go wrong, so long as whatever you do to one side, you do to the other, it's right. It might not be useful, but it's right. So don't be frightened to try things. If you think, well, maybe multiplying by something will help me on this side, that's fine, try it, so long as you do the same thing on this side, multiply the same thing, and so on. So let's have that in mind when we go through solving some equations. And I've picked some out of the text. There's a chapter on solving equations. And here's one I picked. 6x plus 1 equals 2x plus 9. I want to find out what x is. I want to find x. So let's look at this, that side and that side. And I sort of think about looking at one of the sides here, say the 6x plus 1, and trying to get it to the point where I've only got x. One of the problems is I've got x's on both sides. X is a number, remember, so I've got 2 lots of x on the right and 6 lots of x on the left. So if I were to subtract 2 lots of x from this side here, I'd get rid of the x's on the right hand side. Can you see that? 2 lots of x, take away 2 lots of x, get rid of it. That would leave only 9 on this side. Well, that's better, because I've only got x's now on one side. If I take 2x away from this side, I must take 2x away from that side. 6x, take away 2x is 4x. I could decide I'm going to subtract 6x from both sides, and then get rid of the 6x here. Not as useful, not as helpful, because why? I'm left with a negative 4x on this side, yes. So it would work. Remember, whatever you do, as long as you do the same to both sides, it's okay, it would work, but it wouldn't be as useful because I'd be left with a negative number, and I don't want that if I can avoid it. So subtract 2x from both sides, I end up with 4x plus 1 equals 9. And I look at it and I say that looks better than it did before. Looking at it again, I can see that if I subtract that 1, I'm going to be left with just 4 lots of x on this side. That would be useful to do. So I could subtract 1 from both sides. And that would leave me with 4x equals 8. I could decide to divide by 4 to get rid of this, because I only want x. So if I divide by 4, that would work too. But I would have to divide everything by 4. That would mean I'd have to divide this by 4 to get rid of it. I'd have to divide that by 4 and that by 4. So if I divide, I have to divide every term by 4. It would work, but 1 divided by 4 quarter, 9 divided by 4, either a decimal or as 2 1/4, not so helpful. So best step, subtract 1. 4x equals 8. Divide now. Now divide both sides by 4. X equals 2. And that's the sort of process we go through. It will always work. Whatever you do, so long as you do it to both sides, it will always work. For example, if I were to go to here, back to here, 4x plus 1 equals 9, and I did decide to divide by 4, I'd have x plus 1/4 equals 9 quarters. And then I'd subtract this 1/4 from both sides. X equals 9 quarters, take away 8 quarters. Sorry, 1/4 is 8 quarters. 2. Same answer. But I think you'd agree, not quite so straightforward. So the steps, which step you choose, and we'll look at some more complicated ones, of course, all comes from practice. And if you're looking at doing something to one side and seeing what effect it has, and you end up with something that looks worse, you think, than what you started off with, it probably is not a useful step. Not wrong, just not useful. There's another one. Now I've got two ways to go with this. What would you suggest? Expand the brackets. Looking at the left hand side, 3 is multiplied by both of the terms inside the bracket. 3 times x is 3x. 3 times 2 is 6, equals 9. What would we do now with this one? Add the 6 to both sides. Add the 6 to both sides, yeah, is the way to think of it. Okay, add 6 to both sides. 3x equals 9 plus 6 is 15. Divide both sides by 3, x equals 5. Yeah. What's the other way I could go about it? Divide both sides by 3. Yes, look at this. This left-hand side, if we look at it, it's 3 multiplied by what's inside the bracket. What's inside the bracket is a number, x minus 2 is a number. So this whole number, x minus 2, has been multiplied by 3. So why not divide by 3? Don't bother to expand out the brackets. In a more complicated example, it might be a bit of a faff to multiply out those brackets. So divide by 3, and I end up with x minus 2 equals 3. Dividing both sides by 3. And then, well, how do I get x? Just add 2 to both sides. X equals 5. Same answer, look. So neither of them is correct. They're just different ways to do the same thing. Here's another one. This one's worth some discussion. If I've got a fraction, let's think about this for a minute. So some preamble over the side here. It's fractions here. X is a number that we don't know, the denominator of the fraction on the left-hand side. So let's just remind ourselves of the sorts of things we can do with fractions. 2/5 is the same as 4/10. So I can flip both of those, this side and this side. Invert both fractions and write down that 5 over 2 is 10 over 4. That's still true, look. 5 over 2, 2.5, is still the same as 10 over 4, which comes out to be 2.5 as well. I can do that. So that's something about fractions that I've got in my head that might come in useful. However, I remember this. I think you'll agree that that's correct. A fifth plus a fifth is 2/5. However, if I invert both sides, does not equal 5 over 2. And so if there's more than one fraction on both sides, I can't use this invert trick. So long as you remember what you can and can't do with numbers, you can apply those to algebra, to equations, because at the end of the day, these letters are numbers. So whatever I can do with numbers, I could do with the equation. So if in doubt, try it. That's why I still do that now every now and then. Is that right? This valid? Is it valid what I'm trying to do? I'll try it on the side here with a number, and if it works with that, then it's probably going to work with the equation. So one good way to go about doing this would be to invert both sides so that the x is on the top, and I can write x over 3 equals 5 over 4. Now at least the x is on the top. X has been divided by 3. I've divided x by 3. So how do I get rid of the 3? Times by 3, yes, the inverse operation will get rid of it. So multiply both sides by 3. Multiplied by 3, they cancel. Multiplied by 3. So x equals 5 3 to 15 over 4. Note I'm not multiplying top and bottom by 3, only the top. Again, that comes from fraction work. If I multiply two fractions together, 2/3 times 4, that doesn't mean I multiply the 2 by the 4 and the 3 by the 4, the numerator and the denominator. If we think about it, what's implied and is never stated is that this means 4 whole ones, 4 over 1. And when you multiply fractions together, you just multiply top numbers and bottom numbers. So effectively, you're only multiplying the numerator by 4, not the denominator. And that's what I've done here, look. Don't fall into that trap. All these little traps you can fall into, especially when you first start off with these things. I could do this a different way. And this is something I might decide to do instead. So another way of doing this, whenever the thing you're after is underneath, in this case x, I can multiply both sides by x. That means I will end up with 3 equals 4x over 5. It's as though the x has come up from underneath and gone on top on the other side, which is what people often think. You know, just move to the side and put it on top. But be careful about little sayings like that. You know, just you can switch it from one side to the other, move it to the top, because it doesn't always work. What you're actually doing, you've got the x underneath, so I'm multiplying both sides by x, so they cancel out, leaving just 3. So if I had something like 3 over 4 minus x equals 4/5, then it might be a good idea to take this whole expression, 4 minus x, and multiply both sides by it. If I multiply this side by 4 minus x, they can cancel. The whole thing cancels. So long as I remember to multiply the other side by 4 minus x, that would be okay. And then at least the x is on the top. And then I might think about multiplying by 5 to get rid of the 5 underneath, and so on. There's lots of ways I could go from there. Here's another one. So this one I picked out because of it means I can highlight a few points. If we look at it, we've got these yucky fractions again. And on top of that, the y that we're after, the number y, is on both sides. So I remember what I did at the beginning. At some point, I'm going to want to subtract some y's from one side, so I get rid of them on one of the sides, trying to leave a positive number. But what do I do about these fractions? It's always true that if I want to get rid of a number that's underneath, this means, underneath here, divide by. 2y over 5 means 2y divided by 5, doesn't it? Okay, that's what it means. It's like a ratio. And so, if I want to get rid of divide by 5, multiply by 5. But I would have to multiply every term on both sides by 5. So 5 times 2y over 5, they'd cancel. But that's 15 over 4. 5 5s are 25, and I'd have to times that by 5 and this by 5. Every term on both sides I'd have to times by 5. But it would have the advantage of getting rid of this 5. And then I'd say, okay, that's worked. Now let's get rid of the 4. So I'd multiply every term on both sides by the 4, and that'd get rid of that 4. And then I'd multiply every term on both sides by the 20, possibly. It depends on what I'm left with, and so on. But from fraction work, I could think of a number that's common to all, a common denominator, a number that all of these go into and multiply by that. And 20 is a number that they all go into. So I could multiply all 1, 2, 3, 4, 5 terms of this by 20. And that would maybe save me a bit of time. Let's see if that works. So I'm going to multiply both sides by 20. Because I've seen this shortcut. There's a common denominator. It doesn't always work, but it's going to in this case, hopefully. So I'm going to have 2y over 5 times 20. Times 2y over 5 plus 20 times 3 over 4 plus 20 times 5 equals 20 times a 20th minus 20 times 3y over 2. If we look at this, first thing to note is if I times this fraction, 2y over 5 by 20 here, 20 means 20 over 1, remember. And so, actually, if I multiply out the top and the bottom, I have 20 times 2 is 40y over 1 times 5 is 5. In other words, if I've got a 20 there, it's as though the whole thing is like that. So I can extend the line. 20 times 2y over 5 is exactly the same as 20 times 2y all over 5. As this is exact 20 times 3/4 is exactly the same as 20 times 3 all over 4, and so on. So actually I can just multiply tops out. But another way of looking at this is, can I simplify the fraction? Yes. Can I think of a number that goes into 5 and 20? 5. 5 goes into 5 once, 5 goes into 20 4 times. I can simplify here, look. 4s goes into 20. 4s goes into 4 once, and 4s goes into 25 times, and so on. That's why we picked 20, because it was a number that they all went into. So I can simplify the fractions, and they end up with 8y plus 15 plus 100 equals 1 minus 30y. And if you're looking at this, just check you can see those numbers all work. Now I use the idea in algebra of collecting like terms. I can collect all the things that are the same together, all the y's together, all the numbers together. 15 plus 100 is 115. So I can say that 8y plus 115 equals 1 minus 30y. Now, another thing I notice is that this negative, that's minus 30y. So if I were to add 30y, whoops, oh yeah, it doesn't like those zeros. If I add 30y, then that will cancel that out, won't it? Minus 30y plus 30y is gone. So add 30y to both sides. 30 plus 8 is 38y plus 115 equals 1. Then I'm in the territory where I can carry on now. I can subtract 115 from both sides and then divide by 38. I'm going to get a negative answer. So assuming I've not made any mistakes along the way, which is entirely likely when you're doing these sorts of things, so be careful as you go through them. The idea will work. What I've done is I've done the same thing to both sides, and if I've got fractions, I try and get rid of the denominators, the numbers underneath, by either multiplying by each denominator in turn or thinking of a common denominator. And as I mentioned already, if inside the denominator you've got your unknown, like y, it was here, say, then multiply by y and you'll have the y on the top, which we did in the previous one. In the textbook, if you've got an old, I think of the version 6, I'm not sure, you will get on page 66 more equations to solve. Look, there's some you could have a go at, and we're going to have our tutorial sessions when we finish this lecture, so you can have a go at some of those if you want. So the chapter in the textbook on solving equations, anyway, look at those. They start off simple and then get harder, and in the Maths at College site you'll see the solutions to many of them, video solutions, so you can look at them. Okay.